Hello scholars, I hope you all are doing well today. For this lesson we're going to be covering transforming functions. Transforming or transformations should sound familiar to you from geometry when we talked about translations, rotations, and reflections, as well as dilations. We're going to be applying some of the rules that we learned back then to transforming functions, especially graphs of functions. So hang in there, take good notes, and do your best. Let's get going. Last year in geometry, we learned about 4 types of transformations. One was translations, another was reflections, third one was rotations, and lastly, we learned about dilations. Now, translations, reflections, and rotations, as you may remember, are called congruence transformations. That means when we translate, reflect, or rotate a shape, it is congruent to the original figure. However, a dilation changes the size of the original figure, so the new figure, since it has a different size, it is not congruent to the original. So translations, reflections, and rotations can be grouped together, but dilations are in a category of their own. Let's review translations, reflections, and rotations, and then we'll review dilations a little bit later. Dilations are like a slide, like a shift. And you see in the first example, that figure is being translated to the right 6 units. You see in the second example, the original figure is being translated to the left 6 units and up 3 units. We could also say that it's being shifted. Keep that in mind when we talk about functions later. Reflections occur when a figure is flipped. So you see in the first example, the original figure is flipped across the y-axis, and the x values of that original figure become opposite. You see in the second example, the figure is reflected across the x-axis, so then the y values become opposite. You can look at the rules for rotations on your own, but they're not actually going to apply to today's lesson when we discuss transforming functions, so you can breathe a sigh of relief. Now let's talk about translations, which we'll now call shifts, as well as reflections of functions. Take a second to write down these definitions and the formulas, and then I'll try to make sense of them as we move forward. A vertical shift, that means the graph of the function shifts up or it shifts down, and that depends on the value of k that you see here in the formula. F of x is essentially just y. F of x is the same as y. So whatever we're adding to y, we're adding k to y. K is a positive number, then the y value is going to increase. The function is going to go up. If k is a negative number, then the function is going to decrease, and so the function will shift downward. So you see that in that formula, the x value will stay the same for a vertical shift, but the y value is going to change. Again, if k is negative, then it'll decrease, because if we say y plus a negative number, that's like subtracting. Shift is performed on a function. The points on the function are either going to shift to the left or to the right. So the whole function will shift to the left or to the right. Now let's look at that formula. It says f of x minus h. And then we look over here and we see whatever value of h is added to the x value. Because remember, the x values are left and right. We have f of x plus 1 on this graph. So the original function f of x is being shifted to the left, it seems, and we can see that right here. It's being shifted to the left by 1. But this says f of x plus 1. Shouldn't that make it go to the right? Well, we'll get into this more as the semester goes on, but we see that the formula is f of x minus h. So that means h in this case is negative 1. So follow with me. Substitute negative 1 in for h. X minus negative 1. Well, that's going to be x plus 1. X minus negative 1 equals x plus 1. So h is negative 1. Now, look, we're saying x plus negative 1. H is negative 1. We're saying x plus negative 1. So that means we'd have x minus 1. All of the x values are shifting to the left by 1. So let's look at how this point is shifted here. First we have 1, 1, the point we looked at earlier. It shifts to the left to become 0. The x value is decreasing by 1, so that point becomes 0, 1. Points on this function are shifting to the left 1. The whole function is shifting to the left 1. If it was f of x minus 1, they would actually shift to the right 1. So reflections will work just like we learned in geometry. The only thing different is this function notation here. So we have negative f of x. That really means negative y, because we said f of x isn't y. So negative f of x is negative y. Remember, in geometry, we said when you reflect over the x-axis, you make the y values opposite. So that's what's happening here. For reflection across the y-axis, the x values become opposite. And you see inside those parentheses in our function notation, the x is becoming opposite. So we see negative x in those parentheses. So when you reflect across the y, the x values become opposite. So let's transform the function in this graph. First, we're going to shift it, it looks like to the left, and then we're going to shift it up. We're going to shift it left 2 and up 1. Because remember, x minus h, so that means h is actually negative 2, and k equals 1. So we're going to take the x values and subtract them by 2, and we're going to take the y values and add 1. So let's do that to every point. So I'm going to go left 2, up 1, 2, up 1, 2, up 1, up 1. Those dots. That those lines are completely straight. Let's reflect this function across the x-axis. Y values on this function are going to become opposite. Or you may remember from geometry, you can just find the distance to the x-axis. So this point is 1, 2, 3 units away from the x-axis. So I'm just going to go 1, 2, 3 units away on the other side of that axis. So I'm going to do that to each of these points. Connect those dots. Reflect across the y-axis. So just like I did with the x-axis, I'm just going to find the distance these points are from the y-axis. So this point here is 4 units away from the y-axis, so I'm going to go another 4 units on the other side. I'm going to do that to each of these points. Connect those dots. Now I know with 4 different functions on that graph, it may look a little messy, but I hope that was a helpful example for you. Finish up by covering stretches and compressions, but we need to review dilations from geometry before we can get there. The picture to the left, triangle ABC is being dilated to become larger. This is an enlargement. When the scale factor, which is k, is greater than 1, the triangle is going to get bigger. And in this case, the scale factor is actually 2. The triangle is getting twice as big. Now on the right side, we see a rhombus ABCD. It's actually shrinking because the scale factor is less than 1. In fact, in this case, the scale factor is 1/2. So stretches and compressions of functions are going to work similarly to dilations. Second, to write down these notes, and then we'll move forward and make sense of them. For a vertical stretch, it's like the function is being pulled upward. For a compression, it's like it's being pulled close to itself, like into itself. With horizontal stretches and compressions, when it's stretched horizontally, the function is being pulled to the left and right. But when it's compressed horizontally, it's being pushed inward, like so. A is kind of like the scale factor, except for a vertical stretch or compression, that scale factor is only being applied to the y values because it's vertical. Y are the vertical values. So you see our notation is k times f of x, or k times the y values. For horizontal stretch or compression, we're taking that scale factor k and only multiplying it to the x values. So it's f of k times x. K is inside the parentheses, being multiplied just to the x values, or the horizontal left and right values. In 1, it's going to stretch. When k is in between 0 and 1, so like a decimal, like 0.25, or like a fraction, like 1/3, then it's being compressed. Form this function by stretching and compressing it. Number one, the f of x values are being multiplied by 1/2. That means the y values, f of x, right, are being multiplied by 1/2. So in this case, the x values are going to stay the same, but the y values are being multiplied by 1/2. So this point here is 4, 3. So the x value is going to stay the same, but the y value is going to be multiplied by 1/2. So 3 times 1/2, or 3 times 0.5, is 1.5. So that new point is going to be 4, 1.5. Point will transform to 2, 1.5, 1, negative 1. So we're multiplying negative 1 times 0.5. So then this point is going to be 1, negative 0.5. Is negative 3, 4. So we're multiplying the y value 4 by 0.5. So our new point is going to be negative 3, 2. I hope you can see it's been compressed vertically. It's been pushed in just like this, like squeeze. So for number 2, the f of x values, the y values, are being multiplied by 2. So in this case, they're going to stretch since that scale factor is greater than 2. So let's look at these points again. We got 4, 3. Well, the y value is going to double. So instead of 3, it's going to be 6. Now I'm going to go off my graph a little bit here. This next point is also going to double. So this third point, 1, negative 1, is negative 1. So we're going to say negative 1 times 2, which would give us negative 2. We have negative 3, 4. So 4 is the y value, and we're going to double that. So then we'll have negative 3, 8, which is going to be way up here. Now I'll connect the dots. The red function is the vertically stretched version of the original function. Now let's look at number 3. Looks like we're going to be compressing the function horizontally because the x values are being multiplied by 1/2. Now I'm going to clear off these functions so you can see this one a little more. Horizontal compression, we're going to be multiplying the x values of these points by 1/2. So let's look at this point on the right. We've got 4, 3. The x value is 4. So we're going to say 4 times 1/2. Well, that's going to be 2. So our new point is going to be 2, 3. And I'll plot that. I'm plotting that point right on top of that other point. Now let's transform that point that I just plotted on top of. So that point was 2, 3. I'm multiplying the x value by 1/2. So that's going to give me 1, 3. Now I'll plot that point. Point 1, negative 1. Well, 1 is the x value. 1 times 1/2 is 1/2, or 0.5. So I'm going to plot that right in between 0 and 1. Stays the same. And lastly, I'll do the same thing for the last point, negative 3, 4. So we're multiplying negative 3 by 1/2. Negative 3 times 1/2 is negative 1.5. So my new coordinates will be negative 1.5, 4. So I'll plot that. I'll connect the dots. Our final step. Forgive me for those squiggly lines. But I hope you can see how the horizontal compression squeezed it inward. It's like compressed inward. If this was a horizontal stretch, it would have been pulled outward horizontally. I hope this was helpful for you. If you have any questions, rewatch parts of the video if you need to, or look back through the slides. Come prepared for your next class with questions and prepared to work. Good work today. Thank you, collegiate scholars.